Hi there, everyone. So today I'm looking at assignment 24, and actually we're going to start with the in-class worksheet entitled Oil and Wolves. Okay, oil is being pumped continuously from a certain well at a rate proportional to the amount of oil left in the well. Oh, isn't that interesting? Well, let's think about this. The rate is proportional to the amount of oil in the well. Okay. Initially, there were 1,000,000 barrels of oil in that well. 6 years later, there were only 500,000 barrels of oil in that well. It will no longer be profitable to pump oil when there are fewer than 50,000 gallons. All right. Write an equation for y, the amount of oil in the well at any time t. Well, that means they need me to solve this differential equation. Let's do that. Oh, I guess we have to divide by y. And so we've got now 1 over y dy equals k dt. We integrate both sides. Here's ln of y equals kt plus c. Please make sure that c shows up as soon as you integrate and not later. Oh, there's nothing sadder than, well, there are many things sadder than a late arriving t, but in solving differential equations, there's not a lot that's sadder than that. Except, I guess, not showing the separation of variables. We want to exponentiate now. Okay, and that's going to bring us to absolute y equals e to the k t plus c. Again, this plus up here means I can rewrite this as e to the k. Oops, sorry. Rewrite this as e to the c times e to the kt. Right? Because if I'm multiplying and the bases are the same, I can add those exponents. Great. And because I have absolute value of y there and I don't want absolute value, I just want y, I've got to put that plus minus there. So let's say that plus minus e to the c is just some number equals a. So now I can write y equals a e to the kt. 6 points out of 54, almost always. Be prepared to solve that differential equation. Now, if I plug in a 0 for t and 1,000,000 for y, I soon find out that a really is the initial amount like I suspect it is, and now I can write this model. Except we still have a k here. No worries, that's what this second ordered pair is given to us for. 500,000 equals 1,000,000 e to the k times 6. So I divide by 1,000,000 and get 1/2 e to the 6k. Let's take the ln of both sides. And so we've got 6k equals ln of 1/2. So our k value then is just ln of 1/2 over 6. So I think we can write this model. Y equals 1,000,000 e to the ln of 1/2 over 6 t. Now, here's something important. Maybe it's worth thinking about. The amount of oil in the well is decreasing, so I need exponential decay, which means since my base is bigger than 1, that this exponent has to be negative. Right? I need e to the negative x kind of thing going on here. Well, is this k value negative? Yes. And how do I know that? Well, if I think of the ln graph, it's vertical asymptote at x equals 0. And this is the point x equals 1. Well, here's 1/2. And so the ln at 1/2 produces a negative number. I have a negative divided by a positive. I still get negative. Good. Okay, so we've got our model. And that's what they asked for in part A. There's part A. You know, it's interesting. When reading the AP score, it's often we read the question, it says, write the model, and then the next question is, use the model. But what is it that students do? They skip writing the model. Like, they got to this far. And then they say, oh yeah, k equals ln of a half over 6. They go find that. But then they don't put that in there, and they just move on to the next part. At what rate is the amount of oil? Oh, no, I don't want to do that at all. In order not to lose money, at what time t should we no longer pump oil? And so they put the 50,000 in here and the million in here. And they do something like this. This isn't sufficient to earn the point for writing the model. I know it seems like, but Mr. Google, I said that k was this, and look, there's k. Couldn't they just know to put that in there? Yeah, maybe with that arrow, but otherwise no. So there's part A. Part B. Now, part B says, at what rate is the amount of oil in the well decreasing when there are 600,000 gallons of oil remaining? And so I want to say that there's a couple ways that students think about this problem. First of all, they think, okay, well, so I want to find when we're talking about. So they take the 600,000, they plug it in here, and they solve for t. And so t gives them the when. And then it says, at what rate? So then they think, aha, we need y prime. So they find the derivative of this, and they took the time that they got when they set amount of oil equal to 600,000. They plug in that t into the y prime. Well, I want to tell you that, you know what they really want me to do here is to go back to this differential equation, ky. And we found a k, didn't we? It's ln of a half over 6 times y. Well, guess what I'm going to do? I'm going to put that in there. That's the amount of oil. That's the amount of oil. I'm going to plug the amount of oil in here. And so when I do that, I see that, in fact, the rate of change in the oil with respect to time is simply this. And if we figure out what the ln of a half is and multiply that by 10,000, I end up with negative 6931.471. And these would be gallons per year. Amount of time, doesn't say. Yeah, clearly I need to do this, so we're going to say year. Okay? So when there are 60,000 gallons of oil left, what is the rate of change? Well, the amount of oil is decreasing by almost 7,000 gallons per year at that moment in time. Yeah, because we had 6 years. So our time units here are years. Okay, so please don't set this equation equal to 60,000. Don't solve here for t. Don't then take that t value and plug that t value into y prime. Gosh, that's a long way to do that problem. Instead, go to this differential equation. Remember, the rate of change in oil with time is proportional to the amount of oil there remains. That's what they're asking me. And so I think this goes to that place where if your inclination was to solve this equation for t when you put 60,000 in here, I'm wondering if it's because you're avoiding the notation. This is my rate of change in the amount of oil. At what rate is the amount of oil decreasing? Oh, since the question was, by the way, decreasing, we need to make that be our answer. It's decreasing at 69 31 gallons per year. Or it's changing by negative 6931.471 gallons per year. But watch out for that double negative. Don't say decreasing at the rate of this, because that means we're increasing. It really does. Okay, and then part C. In order not to lose money, at what time should oil be no longer pumped from the well? Well, I think this is a pre-cal problem. We're plugging our 50,000 in here. Remember, they said it's no longer profitable if you have less than 50,000. Half over 6 times 2. And we're just going to divide both sides by 1,000,000 here. And so that goes away. Cancel, 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 cancel. And that's 1 over 20 equals e to the ln of a half over 6t. Now I'm going to take the ln of both sides and bring all this down. And I'll flip and multiply to get 6 ln of 1 over 20 divided by ln of 1/2. No, you may not cancel these. No, you may not cancel these. No, 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 no. Just apply your calculator and evaluate it. Okay, next problem. Because it's not just called oil, it's called oil and wolves. Oh, those are adorable wolves in that picture. Let P of t represent the number of wolves in a population at time t equals years, when the population, so change in population with respect to time, is increasing at a rate directly proportional to 800 minus P of t. Now, an interesting thing. Many students, they have absolutely no idea what to do here. No, it's really interesting. No idea. If I write P like this, they say, no problem, can do. Help me. P is a function of time. If I write it like this, you're okay. But if I remind you that P is a function of time, suddenly you're not okay with that? Yeah, I don't get that. So, yeah, I'm going to leave it out so that you understand. Separation of variables, dp over 800 minus p equals k dt. And you know, I just find it so many more students are successful if instead of writing that as a single fraction, they write 800 minus p times dp. Okay? So we integrate on both sides. And over here, we get kt plus c. Yeah. What about over here? So in that last problem where we had 1 over y, we had ln of y was the antiderivative. Yeah, so let's try that and see why I'm sucking air through my teeth. Okay, so this is our theory. Okay, let's take the derivative of this. If I take the derivative of this, the derivative of ln of stuff is 1 over stuff times the derivative of the inside function. I don't have a negative 1 here. I need a negative 1. Don't forget to take the derivative of the inside function. And when you go backwards, don't forget about that negative. So that's my antiderivative equals kt plus c. Now, this thing, well, you got 1 or 2 choices. You can kick that in here and raise this stuff to the negative 1 power. Well, I don't recommend that. Or you could leave it there and try and pretend you know what's going on when you now exponentiate. Or you could just divide both sides by negative. Okay. So this is a constant. You know, that's a constant too. But really, we want to, hey, you know, there was that negative. I'm going to actually say, that's fine, but I really do want that. Okay. So what next? How about we exponentiate? And we get this. Okay. This feels a lot like deriving PERT until it doesn't. So I can still do the thing over here where I have e to the c times e to the kt. Oh, don't forget negative. And on the other side, I've got 800 minus p. Well, in order to get rid of these absolute value bars, I need a plus or minus here. And again, just like we've done with PERT, I'm actually going to say, hey, what about plus and minus e to the c is equal to a? Okay, so now we've got 800 minus p equals a e to the minus kt. And right now, it's still feeling a lot like PERT, except that we have to solve for p. This needs to say p equals. So I'm going to add p to both sides, and I'm going to subtract a e to the minus kt from both sides. Notice I'm subtracting a times e to the minus kt from both sides. Kt from both sides. And so what do I end up with? Well, I'm going to end up with p equals 800 minus a e to the minus kt. Huh. Well, what does that look like? Because that's not PERT anymore. Well, so here's what I'd like to do. I'd like to use the commutative property and flip these. This is a positive 800 and a negative exponential term. So, negative exponential term plus 800. Now, think about this in terms of transformations, okay? This part is exponential decay. This says I'm reflecting my exponential decay across the x-axis. And this shifts everything up 800. Okay, so let's think about that. We have exponential decay. I'm flipping exponential decay, and I'm shifting this graph up 800. Now, notice with this exponential decay, we have this horizontal asymptote here. So I still have a horizontal asymptote when I reflect and shift up 800. Everything moves up 800. And so now I'm going to have this situation that looks like this. Huh, isn't that interesting? It kind of looks like the second half of a logistic graph. Oh. Remember, the first half of the logistic graph looks like that exponential growth function. And then we get to the inflection point, after which our function behaves like this. Oh, well, that's very interesting. And so somehow the logistic model is in fact just gluing those two pieces together. Okay, well, let's see what we're looking for here. If p of 0 is 500, find p of t in terms of t and k. Okay, t and k. So supposedly, if I put a 500 in here and a 0 in here, I'm sorry, a 500 here and a 0 here, I'll be able to solve for a. Let's see how that goes. Okay, so we've got 500 equals 800 minus a e to the minus k times 0. Okay, negative k times 0, 0. E to the 0, 1. 1 times a. And so now I'm here. And I get a equals 800 minus 500. Or 300. So I can rewrite this model as p equals 800 minus 300 e to the minus kt. Well, that's great. That's my model right now. You know, it's funny because often what happens is, say, in the last problem where we're talking about exponential growth, when I gave you y of 0 equals 1,000,000, many of you said, hey, that's the original amount, and just plugged into our PERT model 1,000,000 for the original amount. Guess what? In this type of function, that amount at 0, that's not a. Look, we just showed here. At time equal to 0, there were 500. Did we end up with 500 there for A? Not this time we didn't. Yeah, so watch out for that. If the rate of change with respect to time, in our problem is proportional to 800 minus p, that generates this sort of situation, this thing here. If we had dp over dt equals kp, this is the one where the original amount turns out to be that a value. But that's not this one, so watch out for that. Okay, so we built that model. Oh, wait. Part B says if p of 2 is 700, find k. Okay, 700, 800 minus 300. Please don't turn that into 500. Please. This 300 is attached to some stuff, and this 800 doesn't have that same stuff, so these are not like terms. You may not subtract 300 e to the minus kt from 800. Please don't do that. Okay, but I can subtract 800 from both sides. And I can divide both sides by negative 300. And I can take the ln of both sides and bring this down. So I've got the ln of 1/3 equals negative 2k. Now, k, wouldn't I kind of was expecting k to be a negative number. But look, ln of 1/3 is a negative number. Divided by a negative number, I have positive. K is a positive number. Oh, but there's a minus. Remember when we moved that, we divided both sides by that negative, and we had that minus over there? Yeah, I do. So that takes care of, hey, I was expecting this to be negative. It is negative. K is positive. That's fabulous. So let's write this model out. P equals 800 minus 300 e to the minus ln of 1/3 over negative 2t. Now, yes, I'm going to cancel those. But I know that ln of 1/3 is negative, so I still have that sort of exponential decay going on there. Okay, and then the last question they ask here is, what's the limit of p as time heads to infinity? So here's my model. What happens if I plug bigger and bigger and bigger and bigger and bigger and bigger numbers in here? Well, this is a negative number. So I'm not just plugging in 100, I'm plugging in negative 100, right? Because this is negative. I know it's negative some number, but really the important part for my brain is that this is negative times what I'm plugging in there. So then I'm thinking about e raised to the negative 100 power, right? And that's 1 over e to the 100. One pizza, e to the 100 people come to dinner. Yeah, guess what? This is 0. Even if I multiply by 300, still going to be 0. I mean, yeah, dude, e to the 100? No, 300? Yeah, no one's going to notice 300 times this. This is still 0. And so we've got 800 minus 0. And so my answer to this is 800. And remember what we started with? We started with dp dt equals k 800 minus p. There it is. Right there. That's the 800. Okay. Maybe when we take a look at deriving logistic, we can speak about this a little more. All right, so there we have those first two problems. That's fabulous and fabulous. Ooh, look, you could do a screenshot. And screenshot. Okay, so here we go. I would like to look at a couple of other problems with you. Yeah. And I really should have asked if you wanted me to break this into one video or two. I still have the chance, because there's a bunch of stuff here. So let's see what we can do with this. Okay. The amount of arable land in use increases as the world's population increases. Okay, so the amount of arable land increases as the population increases. Explain why it is plausible that A of t, that's the amount of arable land, satisfies A prime of t equals k a. All right, well, maybe this is hard for you to sort of recognize this, but this over here, that's the same as dA dt equals ka. And so, separation of variables. And so now I've got 1 over a dA equals k dt. And isn't this pert again, right? Whose derivative are you? You are the ln of absolute A, kt plus c. We've seen this movie a lot recently. So I know that what's going on here is this is exponential. And as the population grows, the amount of arable land grows. Okay. So I'm thinking, well, yeah, population is doing this. So why can't more people put more land under cultivation? Yeah, so there's a problem with that. Oh, what are the assumptions are we making about world population and its relationship to arable land being used? Well, do you have a problem with this being our derivative of this? Where the rate of change in the amount of arable land with respect to time, that's what A prime of t is proportional to how much land we've already got under cultivation. Well, what it implies is that over time, this is headed where? What's the limit of this function? Where am I going? That's right. The limit as t heads to infinity of A is infinity. And curiously, there's not an infinite number of hectares on planet Earth. And so I think that's a problem. Additionally, we were asked here, what assumptions are being made about the world population? Well, I think that, since arable land increases as world population increases, I think this suggests that world population is increasing without bound, increasing to infinity. And guess what? We can't do that. You can't have an infinite number of people on this planet. Though part of me wants to see us try and see, does the planet break under the weight of all the people? No, come on, silly, don't say things like that. So, that's all I wanted to talk about, was that maybe PERT isn't the best model. Okay, but we still use PERT for lots of things, and we're always going to teach Algebra 2 and Pre-Cal students about PERT, even though maybe someone else would be better for that job. Okay, next. So let's take this situation. Let's say, sure, I believe in your fantasy. This is my arable land under cultivation. Well, let's take a look. In 1950, true story, there was 1 times 10 to the 9th hectares. And a hectare, by the way, is 2.5 acres. Okay? So In 1950, we had this many hectares of land under cultivation. In 1980, we now had 2 times 10 to the ninth hectares under cultivation. If the total possible arable land on the planet is thought to be 3.2 times 10 to the ninth hectares, when will we be getting there? That could be disturbing. Running out of land on which to plant crops to feed us. Okay, so here, I know that many of you now want to just write PERT. No, sorry, don't do that. You could jump to this if you wanted. And I definitely need to see this. But really, the reason you're having this experience is so that you actually get the practice, so that really, it doesn't take long at all. You're not having to think hard thoughts about this. You can instead just do it because you've done it so many times. Let's say that 1950 is t equals 0 and that 1980 is t equals 30. So there's my initial amount. Of course, I could say this thing over here with plus and minus e to the c equals, I've already used a, so I'm going with b. Okay, so that is this, and I get b. Cool. Now, this is time equal to 0, and this is the amount. If I put the 0 in here and the amount over here, 1 times 10 to the ninth, b times e to the k 0. Oh, look, in this situation, I get 1 times b is this. Yes, this is that situation where that original amount does in fact go here. Doesn't go here in the wolves problem, but it does go here in this problem. 1 times 10 to the ninth. Okay, we still need to solve for k, and that's why they gave me the second point. So I've got 2 times 10 to the ninth equals 1 times 10 to the ninth. E to the k times how many years later? 30 years later. Okay, got to solve this equation for k, so I'm going to divide both sides by this. 2 times 10 to the ninth divided by 1 times 10 to the ninth, that's just 2. And then we get e to the 30k. Well, let's take the ln of both sides. I know, it really did double. The amount of land under cultivation from just after the end of World War II to about the time I was in high school, doubled. Boy, there were a lot of people working to put stuff under cultivation. And so I get ln of 2 over 30 equals k. Great. I come back down here to my model, and I'll put in ln of 2 over 30 times t. So that's our model. Please write the model. Get in the habit of writing the model before you then use the model. Now, we were asked to use this model, though. We were asked to find out when we would get to 3.2 times 10 to the ninth hectares under cultivation. Okay, 3.2 times 10 to the ninth. And now I'm solving for t. So let's divide both sides by 1 times 10 to the ninth. These cancel. 3.2 divided by 1 is just 3.2. So now I'm looking at this. 3.2. Okay, take the ln on both sides. And I can bring this down. So then t, when I'm done flipping and multiplying, is 30 ln 3.2 over ln of 2. And what do I get for that? What do you think? Will it happen in your lifetime? ln 3.2 divided by ln of 2. Okay, and I get 50.342 years. From now? No. From 1950. From 1950, 50 years. This is the year 2000. It's between 2000 and 2001. Raise your hand if you've heard a lot in the news about running out of land to plant crops on. Haven't heard that in the news at all? Huh. Well, how come then? And the answer is because in the 1980s, there were a lot of discoveries or innovations regarding genetically modified seeds. And so now the rice that's grown in much of the planet, it's like 3-4 times as bountiful as it was before the 1980s. So yeah, sometimes we can technology ourselves out of these issues. And this was one of those cases. Hopefully, all of the cases will be these cases, and we can figure our way through them. All right, next. Money in your savings account increases with respect to time at 5% the amount present. Now, I know that your Algebra 2 and Pre-Cal brain is thinking about this problem as, shouldn't I be using this, Mr. Kukla? 1 plus r over m to the nt. No, we're not in Pre-Cal, we're in Calc. Okay? Mr. Kukla, couldn't I use this? Well, yeah, you may well be using that, except, no, because this is calculus. We can't start with one of those finished products. Look, the money in your savings account increases. That means we're talking about a rate. Increases with respect to time. It's a change in the amount of money with respect to time. At 5%, the amount of money present. There we go. There's our differential equation. The money in your savings account is increasing, change in money with respect to time, at a rate of 5% of the amount of money that you have present. How long does it take for your savings to double? Okay, so we want to know, when do we get to 2m? M is the amount of money. I want to have twice the amount of money. Actually, I want 2m sub o. All right, well, let's take a look. We've got dm dt equals 0.05 m. I do my separation of variables. dm over m equals 0.05 dt. And I integrate. Here I get ln of absolute m is 0.05 t plus c. We exponentiate, and we get absolute m equals e to the c, e to the 0.05 t. We take the absolute value bars off by putting plus and minus there. Hey, I don't have that a anymore. So let's say that plus and minus e to the c is a. So I can write my money formula, my money equation, now as m equals a e to the 0.05 t. And we're asking when the amount of money doubles. So according to this notation, I want to know when m equals 2a. What's the time when m equals 2a? So I'm going to replace m with 2a. And now let's divide by a. See, it doesn't matter how much I start with. I just want to know when I'm doubling. And I get 2 equals e to the 0.05 t. Take the ln, bring this down. And so t is going to be ln of 2 over 0.05. ln of 2 divided by, don't forget that parenthesis there before you divide, 0.05. Then you should come up with approximately 13.863 years. That's a long time. Look, I'm just going to say, if you start saving when you're 40, you are not going to get to that place where, you really want to be. Start saving now. Take some of that graduation money. Throw it into a savings account. Throw it into a mutual fund. Start saving now. Okay, so here's what I want to say. In that problem, many of you would have preferred to just say m equals a e to the kt, and we knew that was that. We ended up getting there. But we had to do dm dt equals 0.05 m. Calculus approach, pre-cal approach. So, am I taking the AP pre-cal exam in May? No, I'm taking AP Calculus exam in May. I need to do this. Now, there's one exception to that. And that is if they don't give me the rate. If they don't give me dm dt, if they don't set me up to do separation of variables in a differential equation, then no, I can definitely use PERT. I can jump right to PERT. And I bring that up because a bunch of the problems in our textbook, guess what? They don't set us up this way. They set us up this way. So look, I want you to make sure you can do this. I want to make sure that you're taking that knowledge of solving differential equations and applying it in these situations, okay? However, if you're not given a rate, you can't integrate. If you're given a rate, you must integrate, okay? If you're given a rate. And by given a rate, I mean, if you're given a rate, I mean like here, that 0.05. You know, if I don't have to solve for k, if I'm given a rate, I must integrate. Okay. Do we have any others I'd like to look at? Well, you know, I kind of do. I want to look at Newton's law of cooling tomorrow. But, yeah, let's take a look at these problems, especially since Mr. Paz does not like the textbook I got these from. But I love these questions. They're just wonderful. A yam is put in a 200 degrees Celsius oven and heats up according to the differential equation. dH dt equals negative k h minus 200. Psst, this is the wolves. Right? Because if I push that negative in there, I have a number minus h. This is the wolves. Okay, so we have this. Now, if the yam is 20 degrees Celsius when you put it in the oven, h of 0 equals 20. Solve the differential equation. So here's my initial condition. Here's my differential equation. Let's solve. Okay. So I get 1 over h minus 200 equals negative k dt. Oop, I left out the dh here. So I want to point out something interesting. I see this negative k here. Yeah, it's here for a reason. And notice how, like, when we did the wolves, it was 800 minus p. But here we're doing p minus 800. Because they put the negative out. Why did they take the negative out? Because over here, the antiderivative, you don't have to worry like I did in the wolves problem about that extra negative from the derivative of the inside function. Here, I can just write ln h minus 200. Like they were being so kind. They already moved the negative over there for me. I think that's really nice. I don't know why Mr. Paz doesn't like this book. And kt plus c. We exponentiate. Good. So where does that take us? That takes us to absolute h minus 200 equals e to the c, e to the minus kt. And I can get rid of these by doing this. And wouldn't it be nifty if we said, no, not h sub o. This is like the wolves problem. A equals plus and minus e to the c. So now I've got h minus 200 equals a e to the minus kt. Great, I want to solve for h. h equals a e to the minus kt plus 200. Okay, that's almost my model, but watch out. I still got some stuff here. Okay, so the first thing I want to talk about is this point of information here. So if I plug in a 0 here and a 20 here, what happens? Okay, 20 equals a e to the minus k times 0 plus 200. Well, e to the 0 is 1. So if I want to find a, I have to subtract 200. It looks like a is negative 180. Great. So let's plug our negative 180 in. 200 minus 180 e to the negative kt. I'm a little troubled about this, but, we've taken it as far as we can. I would have liked to have had another piece of information to find k, but right now I've got this situation like we did with the wolves problem. And then in part B, we're told find k using the fact that after 30 minutes, the temperature of the yam is 120 degrees. Okay, so 120, 200 minus 180, e to the minus k times, isn't it 30 minutes? Yes, and aren't the units here in, well, I would have thought the units here were in hours, but there's nothing that says time except for minutes. Yeah, I really want to use 1/2. I'm making time equal to hours, not minutes. Okay, so no, this is not 20. Multiplying before subtraction. So just subtract 200 from both sides. Okay, over 2. Divide both sides by negative 180. And we end up with, I can take a 2 out of both of those and take these minuses off. And so I get 2/9. Okay. So 2/9 equals e to the minus k over 2. Great. We'll take the ln of both sides, and we'll bring this down. So what are we solving for? We're solving for k. ln 2/9 divided by, I'm going to take that step, minus k over 2. Multiply both sides by 2, and divide both sides by that negative, and I get my k value. Or I get my negative k value. Let's do that. Oh, yes, and that's right. You can use that property and kick it up if you would prefer 4 over 81 is negative k. I don't know. Whatever you want. I just need you to be able to solve the differential equation. So, what's our differential equation now? 200 minus 180. E minus k, that's this stuff. 2 ln 2/9 T. There's my heat temperature as a function of time. All right, that was fabulous. But I want to ask sort of an extension question about this. What does this look like when I graph it? So if I put that up there, ln of 4 over 81, it's still a negative. This is exponential to k, reflected across the x-axis and shifted up 200. This is my h of t graph, and this is why h equals 200. Right? That's the temperature the oven is set to. This yam is heating up to the temperature the oven was set at. And so if they asked me, hey, what's the limit of h? as t heads to infinity, we've got that horizontal asymptote there. Okay? All right. So then, let's take a look at this. Can you see it? I'm not sure you can. Let's see. Can you see it? Oh, you can. So here, we've got these choices, and it says graphs represent the temperature. Each of 4 eggs is a function of time, measured in minutes. I used hours. Match 3 of the graphs with the descriptions below, and write a similar description for the 4th graph, including an interpretation of any intercepts or asymptotes. Okay, an egg is taken out of the refrigerator just above 0 degrees Celsius and put into boiling water. Well, oh, and this is Celsius, by the way. So boiling temperature for water, that's 100 degrees. So can the temperature of the eggs, which are going into the boiling water, get above 100 degrees Celsius? Not in any way we're going to notice. So I'm looking now at these two, right? Because in this situation, I'm approaching a temperature of boiling, and in this situation, I'm approaching boiling. So at time equal to 0, temperature is 0 Celsius, which is, that. So I like that. What's happening here? Oh, look, if you squint, you can see it's actually here, and then it increases. Huh. Oh, look, 20 minutes after the egg was taken out of the fridge, it was put in boiling water. Well, so I guess I'm supposed to understand that 20 minutes after I took it out of the fridge, it didn't warm up at all. And it started increasing. That feels a little uncomfortable to me. This is a temperature of 20, not a time of 20. Yeah, I'm pretty comfortable. I'm left to sit on the kitchen table. Oh, the egg is taken out at time equal to 0 and left on the kitchen table, and it heats up to room temperature. Oh yeah, that's room temperature. Okay, and this one. 20 minutes after the egg is taken out of the fridge, it's put in boiling water. So, yeah, that's really weird. 20 minutes after the egg in part 1 is taken out of the fridge. So 20 minutes have come. Oh, after 20 minutes, we took another egg out of the fridge and we heated it up in the water. Okay, so B is this one. A is this one. C, the egg is taken out of the fridge at the same time the egg in part A is left to sit on the kitchen table. This one, because we're taking it out and it's just going up to room temperature. So you need to write a little story for that. I would love to hear your stories. If you watch this video, if you hear me saying these words, you should message me in GroupMe and let me know. And it'll be great because I won't have a clue as to what you're talking about. Okay. Well, look here. Wolves, check it out. It really was an AP question. And I want to say that most students are really uncomfortable with deriving anything other than PERT. And here it is. P is increasing at a rate directly proportional to 800 minus PT. I got to set up that differential equation. I've got to solve that differential equation. Yeah. So, please keep that in mind. I'm not making this stuff up. There's the AP question. All right, well, I think we've got plenty done for day 1. I hope this was helpful. I hope you learned something from it. And I look forward to taking a look at our next video, which does, in fact, have lots of dead bodies. So, yeah, bring your CSI gear to the next video. Take care, everyone.